Next paper is on multiple shape correspondence by dynamic programming, authored by Sahillioglu and Yemez, and the paper is going to be presented by Yusuf.
Hi, my name is Sahillioglu, and I am coming from Turkey, Computer Engineering Department of Middle East Technical University, to present our work titled Multiple Shape Correspondence by Dynamic Programming. This has been done with my advisor Yemez, who is from another good university in Turkey, Koç University. Our problem is shape correspondence between a collection of shapes. So we have multiple shapes, so we are attacking multiple shape correspondence problem. The key idea is minimization of the overall distortion, and the word overall needs special attention here, and I give it with a simple example. So consider this very simple algorithm to solve the multiple shape correspondence problem. Pick the minimum distortion map between each consecutive pair, and then for the non-consecutive pairs, using the transitivity rules and map compositions, the maps are implied, defined. So if I have correspondence from S1 to S2 and S2 to S3, then by transitivity I already have from S1 to S3. So with that, I can find all pairwise correspondences. But there is a problem. There is no guarantee on the overall distortion, because distortions of the maps between the non-consecutive pairs like S2 and S5 can be very high, because I don't have any explicit control on them. I just have explicit control on the consecutive pairs. So this is where our algorithm kicks in. And we explicitly control all shapes efficiently with dynamic programming. This is good. This is a good thing to work with, because it leads to cool graphics applications like them. You all know them, so let's go. So contribution of the paper is, the first one is we are improving pairwise correspondences. So take this example, for instance, on the right. I am finding correspondence between S1 and S2 in isolation, and S2 and S3 in isolation. And you can see that there is a symmetric flip going on in this pairwise matching. This is very natural, and it happens frequently, especially at the coarse level like this. Because the distortion of this map and the distortion of the ground truth map is very close, so you can easily be confused. So here is our approach. We are considering all shapes at once. So while matching S2 to S3, I am also considering the other parts of the framework, the collection. So here you can see that I am preferring a slightly worse mapping in terms of the distortion value. However, in total, the sum of all distortions are smaller than this summation, the black plus red plus the implied green. So it is good to inject the collection information to the process. Another contribution is we are presenting an algorithm which explicitly minimizes the overall distortion while enforcing consistency. And consistency is this: a set of maps is consistent if and only if all cycles of maps yield identity, like this one. So I am starting at the right foot and ending up with the same place that I have started with. So this is an identity map, making this set of maps consistent. And another identity map, so we are good, this is consistent. So with that definition, so we are handling this, and our algorithm is based on dynamic programming, it is running on a novel graph structure, and unlike previous works, no initial set of maps is required. There is no embedding going on, so we are taking action in the previous space where the shapes are defined. We are close approximating the exponential optimal solution, and we are much faster than the alternatives. So the scope of the research is isometric shapes or nearly isometric shapes, and isometric shapes are just articulated version of a human shape, like different poses of a human, and it becomes nearly isometric if you are dealing with semantically similar shapes like a man and a woman. On these isometric shapes, we can exhibit problems like arbitrary topology, scaling differences, noise, and non-uniform triangulation, and we are robust to all of these things. And our method is purely isometric, which is a good thing because isometry is a good clue while performing shape correspondence, because it has this cool property. It has this intrinsic global property that the distance, the metric, like a geodesic distance, are preserved under isometric deformation. So this red length and the green length are the same. So with that, we can exploit that fact to design cool correspondence algorithms. And since our method is isometric, and I have mentioned this overall distortion in the beginning, to be specific, I mean the overall isometric distortion. So I need to define a function that measures the quality of a given mapping in terms of isometric distortion. It is like this. So if I have a map from SK to SL, SK on the left, SL on the right, so to find out how much this mapping deviates from isometry, I traverse the red guy over the black meshes, and here there is non-zero difference of geodesic distances. Here zero difference, non-zero, and zero. And I do the same thing for the other red match, and I go on like this, and I end up with this isometric distortion function, which I will use extensively in the following slides. And this is basically a variant of the isometric distortion measures used in the used in generalized multidimensional scaling work of Ronstein's, or the isometric registration of the Stanford group, or a couple of our works on shape correspondence. Graph representation is pretty important in this multiple shape correspondence business, and apparently and interestingly, all the works so far have used the same graph structure, where all shapes are represented as vertices. They are connected by edges that are weighted by the matching cost of the initially assumed pairwise maps. So there is some initial assumption going on, which we avoid, by the way. So the general theme is they replace potential bad maps with composition of better maps. So in 2009, this trend starts with this work where he replaces each shape pair. He replaces a pairwise map between each shape pair, like S1 and S5, by the composition of maps on the shortest path between those two shapes. So this map can be replaced by the composed map on this outer path. The Stanford group has used the same exact graph, but they have approached it differently. They forced all three cycles of maps on this graph to be identity map. And next year they added additional constraints to the cycle consistency thing. And most recently they established cycle consistency as the solution to a semi-definite program.